In this work, we propose closely interactive human reconstruction with proxemics and physics-guided adaptation. Its goal is to reconstruct closely interactive humans with plausible body poses, natural proxemic relationships, and accurate physical contacts from single-view inputs. The main challenge of this task comes from insufficient visual information caused by depth ambiguity and severe interperson occlusion. Thus, it is difficult to regress accurate body poses and relative positions for interactive humans. In addition, the current deep learning model cannot prevent mesh penetration without explicit physical constraints. To circumvent the problems, we propose to leverage knowledge from proxemic behavior and physics to compensate the lack of visual information. This is based on the observation that human interaction has specific patterns following the social proxemics, and human can still infer plausible poses based on their prior knowledge even when there is severe occlusion. Inspired by this observation, we introduce a proxemics and physics-guided diffusion model to reconstruct closely interactive humans. First, we design a discrete interaction prior to learn the interactive behaviors to provide additional knowledge for the monocular interaction reconstruction. The prior has a dual-branch structure, with each branch representing the motion of a character. Each branch has a codebook learned by VQVAE, which models interactive behaviors. In addition to the codebook, the two branches share the same weights, and they can exchange information with the cross-attention module. With the proposed prior, we then achieve the distribution adaption. Specifically, given a monocular video with interactive humans, we first regress an initial distribution for each person. However, the distribution may not accurately describe the real cases due to the occlusion and visual ambiguity. To refine the distribution, we design a proxemics and physics-guided diffusion model to achieve distribution adaption. The motions drawn from the initial distributions are updated by a discrete interaction prior. The updated motions are then fed into a dual-branch diffusion model to denoise under the guidance of physics and image observations. The denoised motions are then used as the input for the next time step. The adaption takes several diffusion time steps and finally produce accurate results. Our ablation studies demonstrate that the proposed interaction prior and distribution adaption framework are effective. First, the initial prediction is severely affected by visual ambiguity and cannot reconstruct natural interaction. The interaction prior update the motions from initial prediction with proxemic behaviors. Although the prior can produce better interaction, it still suffers from interperson penetrations. With the distribution adaption, our method can refine the results and reconstruct accurate interaction and physical contacts. We also show the intermediate results in each time step during the inference phase to reveal the effectiveness of proposed guidance. The inference contains 5 time steps with the denoising diffusion implicit models. Without the guidance, we find that the denoising model produces slight changes, and the final results still show severe penetrations. In contrast, our model with the guidance can refine the interactions and alleviate penetrations, which demonstrates the importance of our framework. The experimental results show that our method can reconstruct humans with accurate body pose, plausible physical contacts, and realistic interactive behaviors. Thanks for watching.